In this video, we're going to be looking at satellites in circular orbits.
See this?
Yeah.
You know what it is?
Duh. It's an apple.
Good, good, good. All right, watch this.
What the hell? What is this? What is this, some kind of gag?
No, that's orbit.
Huh?
You have your own gravitational pull.
Oh, that's a bunch of crap.
Now back to the Three Stooges.
Aw. Aw.
If I have a body rotating around another body, and the centripetal acceleration that's causing this circular motion around that second body is caused by the gravitational attraction, that's what we call a satellite. The Moon, for example, is a satellite of the Earth. The Earth is a satellite of our Sun. And the Earth has several satellites, several thousand satellites actually, orbiting around it at any moment in time. So these satellites could be used for television purposes, communication, GPS, anything along those lines, weather. So a satellite is an object that orbits around another object, and the centripetal acceleration is caused by the gravitational attraction to that object. So knowing this, and knowing the force formula for centripetal acceleration, we can actually find out a relationship between the mass of our planet or our big object that we're orbiting around, the speed of our satellite, and the radius of our satellite. So if we start out with the formula, F is equal to mv squared on r. This is our centripetal force formula, and we substitute in F is equal to g. We're going to call m1 and m2 little m and capital M. Little m being the mass of our satellite and capital M being the mass of the planet or the body that we're orbiting around. So if we substitute in F, G, M, M on r squared into that first formula, we'd get something that looked like this. G, M, capital M divided by r squared is equal to m v squared on r. If we rearrange this formula now to get v squared as the subject, we would see that v squared is equal to g, little m, capital M, r divided by little m, r squared. Now there's some terms there we can cancel out. We can get rid of the m, so the little m, because they both cancel out on top and bottom, and the squared off of the r squared on the bottom. So we remove the r from the top and remove the square from the r on the bottom. So we're left with then v squared is equal to g, capital M, on r. If we then get v by itself, so we get rid of the square, we chuck in the square root, we get v is equal to the square root of capital G, capital M on r. So here we've related the speed of our satellite to the mass of our planet, or the mass of the object we're orbiting around, and the radius of orbit of our satellite. It is important to note that the radius given in this formula is the height above the planet plus also the radius of that planet. So if we're talking about a satellite around the Earth, we talk about the radius of the Earth plus also the height above the Earth that satellite is. So the whole radius is from the centre of mass of that planet that we're orbiting around. Also from this equation, we can be seen that if we have a certain speed, we're going to have a certain radius. That's because the speed and the radius have a proportionality. The speed is inversely proportional to the square root of our radius. So if we increase the radius, we're going to decrease our speed. If we decrease our radius, we're going to increase our speed. So there is no inclusion of the mass of our satellite in this equation, so we do not take that into account when calculating the speed of our satellites or our radius. we can calculate the period of our satellites using the formula that we worked out back in centripetal motion. V is equal to 2 pi r on t. If we then rearrange this formula and substitute it in, we can calculate the period of our satellites. So the possible orbits of our satellites have to coincide with the centre of mass of the thing that we're orbiting. This comes from the centripetal acceleration and Newton's third law of motion. So the centripetal acceleration is given by our force of attraction, so Newton's law of universal gravitation, and that states that the force is acting along the line joining the two centre of masses. If we do not have the forces acting on the line joining the two centre of masses, then the force is not going to be correct and it's going to be not following uniform circular motion. So, the only possible orbits we can have on a satellite is where we are joining the line that's connecting our two centre of masses. So, we can go around the equator, straight around the Earth. We can go on an angle. As long as we're covering, we've always got the line of our two forces joining the two centre of masses. We cannot just be constantly orbiting, say, around the poles or a certain area, such as we can follow America around the world or follow Australia around the world. We can't just do that. We have to go around the centre of mass of the Earth. So the only possible orbits we can have are where we have a line joining the two centre of masses. So the satellite has to go around the centre of mass of the Earth. Geostationary satellites are satellites where the satellite is constantly above the same location of the Earth, no matter where it is in its rotation. So I've had a geostationary satellite that was above, say, Indonesia. The period of motion of that satellite is going to coincide with the period of rotation of the Earth. So it's going to be 24 hours for rotation of the Earth and 24 hours for a period of rotation for that satellite. So the satellite is always pointing in the correct spot, no matter what. It's always going to be above that location. Geostationary satellites have to be on the equator. If we don't have them orbiting around the equator and they're off skew, not going to be above the same location every time. So geostationary satellites are always on the equatorial plane, same as the equator. So geostationary satellites have a large radius. We have such a large radius because we need to have a period that is equal to 24 hours. So we can calculate this radius using the two equations I told you before. V is equal to 2 pi r on t, so that's the period formula, and also the equation that we derived. V is equal to the square root of g, capital M, on r. If we substitute these two in and rearrange them, we can find out that the radius can be calculated using this information. So the radius will end up being about 36,000 kilometres for a geostationary satellite. So that's a very large radius. So you can do these calculations using these two formulas and rearranging them. So geostationary satellites are generally not used for imagery for, say, meteorology, so weather prediction, or for surveillance. The reason being is that the cameras that we have on these satellites would not be able to achieve a high resolution or a nice, clear, very detailed picture of what we're trying to look at, because the radius is so far away. Whereas if we had a low altitude satellite, it'd be travelling faster, so it'd be able to cover more of the Earth in a shorter period of time. And it's also closer to the Earth, so the cameras don't need to be such high power that they get the same resolution. So we can have a lower powered camera for the same sort of process, saving us money in that sort of sense. But if we still have a high powered camera, we'd get even higher resolution again. So low altitude orbits are used for weather satellites and surveillance satellites, where we can achieve a high resolution of the pictures that we can get from these satellites. So the fact that they're closest to the Earth, so they have a smaller radius, means they're travelling at a higher speed. The higher speed means they might be able to, or they will be able to have a shorter period. So it means they might be able to rotate around the Earth twice in one day possibly, depending on what the radius is. So this is helpful for, say, the monitoring of, say, if we had a bushfire out of control in one spot of the Earth. If we have a satellite that's going past it twice a day, we'll be able to find out how that is spreading through the satellite imagery. Also, if we had a big tropical storm forming over the Pacific Ocean, for example, we can track the movement of this storm and then possibly warn the countries that are going to be involved with the storm. So, low altitude orbits are used for satellites for basically camera work, so we can achieve a high resolution, so a clearer picture of what we can see what's happening. These don't need to be equatorial, they can go whichever way they need to, simply because we don't need to be over the same spot all the time. Satellites generally travel in a west to east direction. This is because of the rotation of the Earth. Since we're on the Earth, we are also travelling in the same direction as its rotation. The rotation of the Earth is in a west to east direction. So if we fire a rocket to get a satellite up into orbit, we'll find out that it requires less fuel to fire the rocket in a west to east direction to get the speed of the satellite at the correct speed it needs for a certain radius, compared to if we fired it in an east to west direction to overcome the rotation of the Earth as well as getting it at the correct speed to orbit the Earth at the certain radius. So there's an advantage of a east to west direction, is it requires less fuel for our rockets to get the satellite up to the correct speed, because it's already travelling at a certain speed as it is sitting on the Earth. So the key points from the video. The speed of a satellite can be calculated using v is equal to the square root of g m on r, where m is the mass of our body, r is the radius of the orbit of our satellite, and v is the speed of the satellite. So we need to know how to derive the formula as well as using the formula. A geostationary satellite is one that's always above a certain location of the Earth, no matter where it is in its rotation. So geostationary satellites must have a certain radius away from the Earth to have the same period as the rotation of the Earth. So we can work out the radius by using the formula v is equal to the square root of g m on r, and using the period formula v is equal to 2 pi r on t. If we substitute that into the other formula and rearrange, we can find out the r. Low altitude orbits are used where we need to have a high resolution image produced. So this is for satellites that are for weather prediction, so meteorology, and also surveillance. So these don't need to be on the equatorial plane, unlike a geostationary satellite that needs to be on the equatorial plane of the Earth, so always above the equator. These can go in any other direction, but generally in an east to west direction due to the logistics involved in trying to get it in an east to west direction. In a west to east direction, we use less fuel in our rockets to get our satellites up to the speed required for our fixed radius that we want. For satellites, the satellite must always orbit the centre of mass of the body it's orbiting. That's because of the centripetal acceleration needs to be directed towards the centre of the motion, and our attraction force, which is our gravitational attraction, is always directed on the line joining the two centre of masses. So orbits of possible orbits of satellites must always coincide with the centre of masses of both the satellite and the body that it's orbiting. So that's been satellites.